Welcome back to another deep dive. Today, I want to start with a mental image. I want you to imagine you are standing in a completely dark room, pitch black.
Okay.
You can't see your hand in front of your face, but you have a flashlight.
A classic setup.
You switch it on. Now, you have this perfect, bright, crisp circle of light on the wall right in front of you. You can see everything inside that beam and, the high definition, the texture of the paint, a tiny spider web, every little crack. You have perfect local knowledge.
But outside that beam.
Absolute mystery.
Yeah.
And here's the problem. What if there's a cliff, a drop-off, or a wall just 5 feet to your left? You won't see it until you literally fall off the edge.
That is a terrifying but a perfect analogy for the mathematical tool we're discussing today.
We're talking about the Taylor series. It's the flashlight of the mathematical world. It's brilliant locally, but it's blind globally. And our mission today is to figure out how to turn on the overhead lights.
Right.
They might be dimmer than that intense flashlight beam, but they show you the whole room, including the dangerous parts.
We're moving from local approximation to global truth. It's a shift in architecture. We're going to stop, adding things up and start dividing them.
We're looking at rational approximation. It sounds technical, but when you dig into the sources, it's actually about predicting the future of a system when your standard tools just break down.
It's the difference between just seeing a curve and understanding the underlying law that created that curve.
So let's start with the local hero we're leaving behind, the Taylor series. Now, I have flashbacks to calculus class, just memorizing these long strings of algebra.
We all do.
1 plus x squared over 2, and so on.
And in engineering and physics, the Taylor series is the absolute workhorse. I mean, it is the standard tool. If you want to know how a function behaves near a specific point, say near 0, you use a Taylor series.
But why is it so popular if it has this flashlight problem?
Because it's safe. A Taylor series is a polynomial. It's just a sum of terms. A plus b times x plus c times x squared.
They're predictable. They behave well.
Exactly. Polynomials are smooth, they curve gently, they don't do anything crazy. If you're designing a bridge or a circuit and you only care about a very small range of operation, the Taylor series is your best friend.
But the source material identifies what it calls a fatal flaw, the wall.
The wall. This is where the safety of the polynomial becomes its downfall. You see, because a polynomial is just a string of finite numbers added together, it can get very large, but it can never, ever be infinite.
Mathematically, a polynomial can't blow up.
Right. It can't model a singularity, and the physical world is full of singularities.
Things like phase transitions, shock waves, resonance.
Exactly. Think of a sound wave turning into a sonic boom, or water turning into steam, or the gravitational forces near a black hole. At those points, the math effectively goes to infinity. The physics blows up.
And if you try to use a Taylor series to model that,
the math simply breaks. It starts giving you garbage data. It diverges.
So the Taylor series is basically lying to you. It's showing you this smooth path right up until the moment you hit the cliff.
It's blind to the most interesting parts of the universe because it's structurally incapable of representing them.
Which brings us to our first section, a shift in architecture. We need a new way to build these approximations if we want to see the cliffs. The notes contrast linear accumulation with nested division.
This is the key mental shift. With the Taylor series, you're doing linear accumulation. You're just stacking bricks side by side. One term, then the next, then the next.
A horizontal expansion.
Yes. But the alternative, the continued fraction, it looks completely different visually.
I'm looking at the slide here, and it looks like a staircase just descending into the page.
It does. It's recursive. You start with a number plus a fraction. But the denominator of that fraction isn't just a simple number. It is another number plus another fraction.
And the denominator of that fraction has another one inside it, and so on.
And it goes down and down, nested inside itself. It's all about this repeated division.
Why is that structure better? Why does nesting the division give us a better picture of the room than just adding terms?
It's about relationship versus accumulation. A sum just, piles up value. But a continued fraction creates this dynamic relationship between the numerator and the denominator at every single step. It allows the function to twist and turn in ways a polynomial just can't.
It captures the global topology of the function.
That's the word for it.
Okay, but we aren't just guessing these numbers to build the staircase, right? There has to be a method. The notes mention something called the Vyskevtov algorithm.
Vyskevtov. It Sounds like a spy movie villain, but it's actually a very elegant piece of 19th century mathematics.
How does it work? I mean, without us getting out a whiteboard here.
The concept is surprisingly intuitive if you think about it as a kind of refining process. Imagine you have a Taylor series, that standard power series we talked about. The Viskovitov algorithm takes that series and essentially flips it inside out.
Flipping.
You take the number 1 and divide it by the series. You extract the part that doesn't change, the constant term, and then you take the remainder, you invert it, flip it over, and you just do it again.
So, divide, extract, invert.
Exactly. Divide, extract, invert, repeat. You are essentially distilling the series. You're taking that linear string of information and refolding it into this deep nested structure.
That's a great way to put it. It's like taking a flat sheet of paper and folding it into some intricate origami shape. You haven't added new paper. You've just changed the architecture to reveal something new.
That's a beautiful way to put it. You're re-architecting the information.
Okay, so we have the theory, we have the staircase, but we need to make this concrete. And the source material uses probably the most famous number in the world to prove why this works. We're talking about pi.
Pi is the ultimate testing ground. It's infinite, it's non-repeating, and it's notoriously hard to pin down with simple numbers.
So let's look at this case study. We apply this continued fraction method to pi. Instead of the decimal 3.14159, we get a list of integers.
Right. You get the simple continued fraction for pi. The sequence is 3, 7, 15, 1, 292, and so on.
I have to say, looking at those numbers, 3, 7, 15, 1, 292, they look completely random. There's no obvious pattern there.
In the simple continued fraction for pi, they essentially are random. That's one of the deep mysteries of pi. But even though the numbers look chaotic, they are incredibly efficient at capturing the value of pi.
This leads us to a term I hadn't heard before, convergence.
A convergent is just a snapshot. Since the fraction goes on forever, you have to stop the staircase somewhere to get a number you can actually use. Where you choose to cut it off determines your convergence.
Okay, let's walk through the stages here. Stage 1, we cut it off right at the start. We just take the 3 and the first fraction part, the 1/7.
Which gives us the very famous 22/7.
The classic. I remember that from elementary school geometry.
It's legendary, and it's actually a very decent approximation. It gets you to 3.142. The real pi is 3.1415, so you're good to 2 decimal places. For building a garden fence, it's perfect.
But we want high precision. We want the deep dive version, so we go deeper. The notes highlight stage 3 as the real hero here, the star.
This is where the power of continued fractions becomes undeniable. If you go down to the third step, including that 15 and that 1 in the sequence, you get the fraction 355/113.
355/113. This number has a name, doesn't it?
It's called Milu. It was discovered by the Chinese mathematician Zhu Chongzi way back in 480 AD. Think about that. 480 AD. And it is a beast of a number.
Okay, how good is it?
It is accurate to 6 decimal places.
6, just from dividing 355 by 113.
Yes. It's 3.141592. It's dead on. And here's the kicker. It's what's called a best rational approximation.
What does that mean?
It means that if you were looking for a fraction to approximate pi, you cannot find a better one with a denominator smaller than 30,000.
Wait, so to beat 355/113, to get even slightly more accurate, I'd need a fraction with massive numbers.
Exactly. You'd have to go to numbers like 52,163/16,604 to do just a tiny bit better. Milu is an efficiency monster. It captures the essence of pi with incredibly simple integers.
That is wild. The notes compare this to the Gregory Leibniz series, which is a standard sum used to calculate pi.
Oh, the Gregory Leibniz series is painfully slow. Just painfully. To get the same accuracy that Milu gives you instantly, those 6 decimal places, you would need to add up hundreds of thousands of terms.
So the ratio is exponentially faster than the sum.
It's not even close. It's the difference between walking to the moon and taking a warp drive.
Before we move on from pi, I have to touch on this hidden beauty section, because we just said the numbers 3, 7, 15, 1 were random, but the notes say there's another way to write this fraction where they aren't random at all.
Yes. This is Lord Bronker's pattern. He realized that if you relax the rules a bit, if you stop forcing all the numerators to be the number 1, you can find a hidden structure.
And what is that structure?
It uses the squares of the odd numbers. 1 squared, 3 squared, 5 squared, 7 squared, just cascading down the staircase. And the denominators become a constant stream of the number 2.
That gave me chills reading it. Pi is related to circles, but here it is, intimately connected to the odd integers, 1, 3, 5, 7.
It's beautiful, isn't it? It shows that the apparent chaos of the digits is just a surface-level problem. Underneath, if you use the right architecture, if you use division instead of addition, there is perfect order.
It's like finding a secret code. Okay, so we've established that fractions win at arithmetic. But this isn't just about numbers, it's about physics. Functions that move and change.
And that is where we enter the world of the Pade approximant.
Help me make the jump. We just did 355 over 113 for a static number. How does that translate to modeling, say, a sound wave?
It's the exact same logic. Think of it this way. Arithmetic is to analysis what milieu is to Pade.
Okay, unpack that a little.
If you apply that Vysogotoff algorithm to a function with a variable with an x in it, instead of getting a fraction of integers, you get a rational function, a ratio of two polynomials. Let's call the top one p of x and the bottom one q of x.
So instead of just a polynomial like the Taylor series, we have one polynomial divided by another one.
Correct. And just like we had convergence for pi, we organize these functions into what's called the Pade table.
I'm looking at the grid in the notes. It looks like a spreadsheet with L across the top and M down the side.
Right. L is the power of the top polynomial, the numerator. M is the power of the bottom one, the denominator.
And looking at this, the very top row, where M is 0, that's labeled standard Taylor series.
And that's the key insight. A Taylor series isn't wrong. It's just a specific limited case of the Pade approximant where the denominator's power is 0, so the denominator is just 1.
It's just the top row at the table.
Exactly. So if you stick to Taylor series, you are effectively ignoring the rest of the map.
You're ignoring the division.
And by doing that, you're ignoring the ability to model the sweet spot.
Which is the diagonal Pade.
The diagonal. That's where L and M are roughly equal. That is usually where the magic happens. That's where you get that milieu effect, but for complex functions.
So why do we do this? Why add the complexity of division? We hinted at it, but let's get into the physics. Why does Pade win in the real world?
It comes back to the superpower, handling singularities.
The blow-ups.
Let's go back to the Taylor series. It's a sum, 1 plus x squared. Can you add up a string of finite numbers and ever get infinity as the result?
No. You can get a really, really big number, but you can't get actual mathematical infinity.
Right. So a Taylor series simply cannot model a pole, a point where the function breaks. It physically can't do it. But now look at a fraction. Look at the Pade approximant. What happens if the bottom polynomial, that denominator q of x, hits 0?
Well, if you divide by 0, the result shoots to infinity.
Precisely. The Pade approximant has a built-in mechanism to create infinity. It can naturally model a pole. If the physical system has a resonance point where energy spikes, the Pade approximant says, I can do that. I just set my denominator to 0 right there.
That is profound. It doesn't just approximate the curve, it predicts the structure of the breakdown itself.
It predicts the location of poles that are completely invisible to the Taylor series. You could be analyzing a data set with a Taylor series, see nothing but a smooth curve, and be totally unaware that you're about to hit a wall. The Pade approximant acts like a radar.
It detects the cliff.
Before you fall off.
This leads to that fascinating concept of analytic continuation. The notes talk about a radius of confidence.
This is the turning on the overhead lights moment we promised. A Taylor series has a strict radius of convergence. Inside that circle, it works. Outside the circle, it's garbage. It diverges wildly.
It flails around.
Yes, but Pade approximants often converge outside that region. They effectively let us see behind the wall where the Taylor series just falls apart.
The graphic in the notes is really striking. You see this tiny circle where Taylor works, and then this massive, weirdly shaped blob extending way out where the Pade works.
That blob is the domain of analytic continuation. It allows scientists to take data from a region where they can measure things, say low energy states, and project it into a region where they can't, like high energy states.
So if I'm a particle physicist and I can only run experiments at low energy, I can use Pade to predict what might happen at super high energy.
Exactly. It's standard practice in quantum chromodynamics and condensed matter physics. You use this rational structure to extrapolate beyond your data. It's not just a math trick. It's a tool for discovery. It lets us peek into the dark corners of that room.
It's the difference between knowing the system works right here and understanding the global topology of the entire system.
Topology is the right word. A sum is local. A ratio is global.
This has been a workout for the brain, but I think the takeaway is surprisingly intuitive. Let's just recap the journey before we wrap up.
Sure. We started with the Taylor series, the flashlight.
Great for local detail, but blind to the big picture and terrified of cliffs.
So we introduced a shift in architecture from linear accumulation to nested division, the continued fraction.
We saw how that structure built by the Viskovitov algorithm creates that staircase that captures data way more efficiently.
We saw that efficiency in action with pi. 22 over 7 was okay, but 355 over 113 milieu was a masterpiece.
A total masterpiece, and we saw that deep connection to the odd squares with Lord Bronker's pattern.
Then finally, we scaled that up to the pade approximate. We realized that by dividing polynomials, we gain the superpower of modeling singularities.
We can predict the poles, we can see past the radius of convergence, we can see the global truth.
Exactly.
The source material ends with a quote from Henri Poincaré that I've been thinking about this whole time. He said, "Mathematics is the art of giving the same name to different things."
It's such a deep thought. We look at a sequence of numbers, we can call it a sum and treat it like a pile of bricks. Or we can call it a ratio and treat it like a relationship.
And just by changing the name, by changing the lens we view it through, we reveal a nature that was completely hidden before.
It makes you wonder, in our own work, in our analysis, even in things like economics or social trends, how often are we looking at a sum when we should be looking for a ratio?
That is the question. Next time you see a trend line that looks smooth and safe, maybe ask yourself, am I looking at a Taylor series that's about to hit a wall? Or do I need a pade approximate to see the singularity coming?
Always check the denominator.
Always check the denominator. Thanks for joining us on this deep dive. We'll see you next time.